There's a number of things that we kind of need to recap in terms of details because they'll be mainly on multiple choice, and also giving you some perspective to like how you approach some of these problems that relate to the strength of the acid, strength of the base, and also why certain ions behave the way they should or the way they do. So it gives you prediction power, right? Understanding why things occur or the behavior they take on generally. So most of the time, if you have a strong acid, give me an example of a strong acid. Nitric, okay? So nitric acid, when it deprotonates, meaning takes an H plus off, what does it make? And nitrate, right? Okay, so this is a strong acid, and what can happen is NO3 can gain the H plus back, right? So it could do that to reform nitric acid, but it will never do that because as soon as the nitric acid forms, it's going to reionize, so it's like a never-ending cycle. So this is likely not attracting the H plus very well. So if you're not able to attract an H plus, would you say that you're a strong base or a weak base? Okay, so this is a weak base, meaning bases like one to form hydroxides in water. Two, they do a pretty dang good job of attracting H pluses because they like to kind of neutralize themselves. Yeah.
So how does it do with the strong acids have weak conjugate bases?
Yes, that's the point here. So what you should see is that all of the strong acids, their conjugates that they make, so the conjugate bases that they make, they're really, really weak bases. They're weak conjugate bases, what we call them. And so the conjugate base is the difference of one H. Okay, so if I ever say what's the conjugate acid base pair, you should say this is the acid, and its base that correlates with it is this, because of the one H plus that's different there. So any other strong acids will do the same thing. They'll form weak conjugate bases. So what about a weak base or a weak acid? Give me an example of a weak acid. Hydrofluoric. Okay, so hydrofluoric, when it ionizes, it makes H plus and F minus, but this doesn't ionize very well. So we're not making a whole lot of this to begin with, but this right here, because we don't make a lot of H plus and F minus, that means...
For interruption, please dismiss current sophomores to the assembly. Last names beginning with E through K. At this
like
time.
Last year.
Thank you.
Or 2 years ago. For me, like years ago. Okay, so this right here is going to do a very, very good job of re-attracting to the H plus, meaning that their bond is fairly strong. So this is a weak acid, but it forms a strong conjugate base because it will force the reverse reaction heavily in the reverse direction because it's so strong or good at gaining the H plus back. Okay, so the strength difference is a point that you should be able to explain. Generally, oxyacids, which have oxygen in it, the higher the oxidation state makes a difference. So a higher oxidation state generally means stronger acid because this right here, which is sulfate, remember I drew it yesterday? And then bear with me because this is not 100%. That's a double bond, sorry. Okay, so there's hydrosulfuric acid. Generally, the greater the number of electrons means you have a larger electron density. That larger electron density.
Teacher, please dismiss current sophomores to the assembly and auditorium. Last names begin in E through K. Again, current sophomores, rising juniors to the assembly and the auditorium. Last names begin in E through K. Thank you.
All right, let's finish this up. I'd like to finish this statement. Whenever you have a large electron density, that means that the bond that's between the O and H here and then the O and H here, the electron density is very large in the middle. It means the electrons are pulling inward. And so as the electrons pull inward, what does it do to that bond right there? It weakens that, and it's able to cleave the H off easily when an attractive molecule comes on the outside to grab the H plus. What's an attractive molecule that's on the outside that's able to grab H plus? Water. Water is a great contender. It's like, hey, we got this extra space. You can jump on with us. And it pulls the H plus off to make hydronium, hence acidic. Okay, so understanding the molecular strengths, bonds, why something's strong together is pretty important. Along with that is the differences between ions and the ability to form an H plus when you are charged yourself. So if you have a plus charge like hydronium, it's very easy to pull an H plus off because you already have a positive and a positive don't interact well. So there's almost like a repulsion of another H plus. If you're neutral though, It's a little bit harder to pull the H plus off because there's not a negative or a positive. I'm sorry, there's not a positive there to counteract that. If you are a negative already, you have a large attraction for something positive. So it's not so likely that you're going to get rid of a positive, because then you get doubly negative, meaning a large ion charge is less likely to donate another charged ion, and then so forth. So this right here is actually, you guys know NH4, what is NH4? Ammonium. Okay, ammonium can be acidic, because what does acidic mean again? Able to donate an H plus. It can do that, but it is a strong conjugate acid because it's the opposite of ammonia, but it's still not as strong as hydronium, not even close. This is like pretty dang acidic in terms of able to form an H plus. This is still not quite as strong. Yeah. Question? Oh, you had a question. Okay. And then so forth, you can see the ion changes again, but the cation of the stronger acid, I'm not sure what I'm saying there. Neutral is a stronger acid than, oh yeah, okay. So something that's neutral, like water, is able to form H plus easier than something that's an anion, because anions attract their H plus as well. So on this right here, this question is in your NSMI. You guys have that out? Or if you need to grab a computer, grab one now. You want to grab it free? I'll tell you guys the K values for this. Well, we'll use some logic and we'll use some K values. This is exercise 3. So what you'll notice is on homework, between today and tomorrow, you'll be doing some of the examples on this NSMI. So if I do them with you, some of them, you're not having to do them by yourselves, which is kind of nice. If I can find example 3. Thank you. It's on page 7 if you're looking. If you have it printed out or if you want to look with a friend. Okay, so I arranged these in accordance with their strength as a base. So that means their ability to gain or accept an H plus. So H2O, first off, what's the word that describes it can act acidically or basically? What's the word that can act both ways? Amphoteric, right? That's amphoteric. Okay, F minus, that is the blank of a weak acid. F minus came from HF. HF is a weak acid. That's the conjugate base. And so you know it's the conjugate base, but it's the conjugate base of a weak acid. Is that strong or weak? Strong. So I'm going to SCB, you guys know what that means. Strong conjugate base. Okay, so that's kind of giving us some relative comparison so far. Cl minus, so here's this water. This is F minus. Cl minus is the conjugate base of a strong acid, so it's a weak conjugate base because it doesn't want the H plus back, because as soon as it gets the H plus back, it's going to reionize and we're back in the same place. Okay, NO2, 1 minus is the conjugate base of a weak acid, so it's a strong conjugate base, yes? Because it's the conjugate base of a weak acid. And then lastly, Cn minus, it is the conjugate base of a weak acid, so it's also a strong conjugate base. So there's something that must distinguish the differences between the strengths of each of these conjugate bases. So I'll tell you the Ka values and give you some indication of these. So, Ka values, where did I put you? There you are. And this is also in the back of your book. You can, if you want to, if you have your computer, just Google a Ka value chart. You can find a lot of them together. So you need the Ka values of everything that's a strong conjugate base. So HF Ka value is, give me a second, they are not in any kind of order. HF, 7.2 times 10 to the negative 4th, okay? Hydrochloric acid, this is a strong acid. What would you say about its K value? Say again? Pretty high. I'm going to go way greater than 1, okay? This is water. I'm not doing that one. All right, so nitrite came from nitrous acid. Sorry, I should have already put these down. Oh, nitrous acid, where are you? Oh, 4 times 10 to the negative 4th. Okay, and then CN, or hydrocyanic acid, or cyanic acid, there's a number of ways to say that one, is 6.17 times 10 to the negative 10. Of these acids that I've indicated, now of course it's for the acidic form of of F. So this is for HF, this is for HNO2, and this is for HCN. Of these 1, 2, 3 acids, who's the strongest acid? Say again? Who has the largest Ka value? Nitrous has a 4. Hydrofluoric has a 7.2. Hydrofluoric, right? So this is the largest of the weak, right? The largest Ka. So largest Ka means that you are a stronger weak acid. Okay? What does that tell you about your strength of your conjugate? It's weaker. Because what's going to happen is your anion you make, so when you dissociate, it's even less likely to turn around and recombine with the H+, because you're trying to push to products. You're trying to push towards the K getting larger, which means that products are favored. So largest Ka value means that products are favored, right? Products being favored means that you have a weaker conjugate base. Okay, and then so forth. So this is like the weakest of the conjugate bases, right? So I'm going to call this the weakest. Who's the second weakest of the conjugate bases that we haven't read here? Okay, so this is the second weakest of the conjugate bases. And then who's the I say second weakest, this might be nomenclature that's weird, but then this is the strongest of the conjugate base, the weak conjugate bases. Oh Lord, okay. I could have probably worded that better, but I think we're on the right page. Okay, so of all these, it says arrange according to their strength. So who's the strongest, or who's most basic? Who's the ability to act most basic? Say again? Hydrochloric, because it's like, heck no, I'm not turning around to regain that H+, because HCl is going to throw me back and make me form Cl- again. So Cl- is the strongest, and the answers are on your paper, guys, but work with me. This is the strongest of the bases because it comes from a strong acid. Okay? Who's the next strongest of the bases? Oh, hold on. Yeah. So this is I said this is a weak conjugate base, which means that's the strongest conjugate base. I'm sorry. It comes from a... No. That's the weakest of the conjugate bases. My bad. We were right here. I just got to figure out which way I'm ordering. This is a weak conjugate base. Okay. This is the weakest. From the strongest acid is the weakest. Let's go this way. Okay. Who is sequentially next then? Okay, because it's kind of neutral. It's able to act as acid. It's able to act as base. This is like for sure going to be from the strongest acid, so it's going to be the weakest conjugate base. Okay, and then who's sequentially next? Say again. Okay, so fluoride. Sorry, I think I said chloride again. Fluoride because it's coming from the kind of largest value of Ka, and then sequentially nitrate, right? Or nitrite, sorry, and then Cn-, because it's the strongest of the weak conjugate bases. Okay, it's kind of interesting to try to wrap your head around that, but I think as you go, we'll be okay. We just need to kind of say those out loud. I think that's one of the harder things to compare because you have to think about usually about 3 or 4 things at one time. All right, so you guys have these examples. We're moving on. This is information I meant to get to you yesterday. I'm sorry I didn't get to you. Oh, I gotta check. We gotta go over homework. Don't forget too far ahead because I'll just keep going. We stop at the end of acids. We'll go over homework. So we talk about pH being a combination of the H+ concentration and negative log. Well, Ka, you can do the same thing with as like we do with H+, and you take a negative log of that, and you can get pKa, which is sometimes the way it's published, to give you indication of how strong or weak that acid is. And you'll probably start to see that eventually. We're going to start getting into bases as well more today, but KBs do the same information that a Ka does, except referring to bases, hydroxides, and so forth. So write down that information for yourself. The devil's in the details, so I'm trying to make sure you see the details. And so this information here, which is saying the lower the pH is the stronger or more concentrated acid. Same thing is about the pKa, the mathematical relationship is the same because of that negative value in the front. The lower the pKa value, the stronger the acid. Because the lower the pKa value means you have a larger Ka. What does Ka refer to one more time? The equilibrium constant for what of acids? I'm going to say dissociation. Okay, so the Ka value, the board is a little off, sorry. The, I'm going to say acid dissociation constant. That's what Ka stands for. And so if you have a large dissociation constant, that means that you're favoring products quite a bit, not so much the reactants, which makes sense for a strong acid because it dissociates a lot. It dissociates closer to 100% than not. And so the same will be for bases. We'll get there shortly. Thumbs up if you're able to move on. Question? Yeah, sorry. So you calculate it the same way you do pH. Okay? All right, then now tell me on homework which ones I need to go over. Say again? So 6, I'll kind of do 6 holistically. 6, 2, 4, and 6? 2, 4, and 6, okay. Try to make this a little bit bigger. Now this is my handwritten key, so forgive me if it's a little scratched. The scans are always not great. But here you go, number 2. 2 said you have combined acid mixture of strong acid and strong acid, HCl and HNO3. This was on your video from Monday, from Monday. If you need to rewatch that for yourself. But you take your moles, which I did millimoles, but moles of the HCl, which delivers H+, moles of the HNO3, which delivers H+, total the moles of, the millimoles of the 2 H's on top, divided by the total volume. Of course, I did millimoles, so I divide by milliliters. That gives me the combined total net H+ concentration. That should have been 0.2. Give me a thumbs up if you got that far. Awesome. So then you had to plug into, you had to do the other concentrations as well. So the HCl delivers the Cl, so I just plugged in HCl, M times V gives you millimoles divided by the total solution volume to get the same, we get 0.13 for chlorine's concentration, and then similar story but with nitrate, and then divide by the total volume to get 0.075 for nitrate's concentration. And then for your pH, you just had to take the concentration of your H+, plug it into negative log, and then that's 0.7, so that should make sense. We have 2 strong acids, so pH is very low. That's good. It should reflect on that. Question 4. Is this the Chateliers, or number 6 was? Number 6 was, right? Okay, well this is this one example, I don't believe I plugged the Ka in your problem set, but you could have looked up the Ka, and again there in the back of your book, there's a whole appendix with that. So Ka of this guy is 1.6 times 10 to the negative 10th, and as this dissociates, it makes, when it reacts with water, now water is a key component. Many times you'll see me not put water here, but you definitely can put water and you'll form H3O+, and then the anion. So phenol, I might need to reread this question, but phenol being 0.25 molar, let's scroll this way. Phenol being 0.25 molar gives you your initial minus x plus x plus x because it's dissociating a small extent, which you don't know. When you solve for x, when you plug into your concentrations, into your acid dissociation constant along with your expression, and solve for x, which I did over here someplace, being 6.3 times 10 to the negative 6, the value of the initial acid doesn't change too much because x is so negligible because it's 10 to the negative 6 versus 0.25, so there's basically no difference there. It's approximately the same as what the little wiggly lines mean. And then your OH concentration is what you had to find, so you had to take Kw, which, what is Kw? What's Kw? What's concentration of hydronium times concentration of hydroxide? It's a constant. Say again? Yeah. You guys would have written this down in your notes from Monday. 1 times 10 to the negative 14. Okay? So KW, if I ever ask for that, it's the water constant 1 times 10 to the negative 14. So that's equal to the concentration of hydroxide times the concentration of hydronium, which is how you solve for one of the variables if you have the other and you don't have anything else, pH, pH, or anything. So that's the variable or value I used down here to find the OH from the H3O. So I did, it's tiny, 1 times 10 to the negative 14 divided by H plus give me 1.59 times 10 to the negative 9 for hydroxide. Okay, so that was 4. And then to show the approximation of the ionization, I did neglect X. Oh, this is the solution in here. I did neglect X, and you could do your percent ionization to prove that it was negligible. And then this was the cyanic acid, 6.2-ish times 10 to the negative 10 was your Ka. So after I give you the Kas, does that give you indication of what you could do from there? Is it just the Ka values? Do look those up. Don't let that stop you. But that's a stronger acid. So basically, this comparison here is saying water, which is amphoteric, it can act as an acid, right? It's a super weak acid, but it can act as an acid. What you can do is to compare the Kas of the acid that's given to you versus the water constant, and whichever one's bigger acts as the predominant acid. And so this Ka, 6.2 times 10 to the negative 10, is greater than the water constant, 1 times 10 to the negative 14. So it's acting as the acid, which you probably assumed anyway. But that's like the background knowledge that applies to that concept. So I think on number 4, am I good? Can I move on? Yay or nay? Talk to me, Buell. Okay. 6. Oops, I'm sorry. I just scooched right past it. Okay, so I heard C and D mainly. On part A, we went through acetic acid's Ka value in class. I think you should have been fine with A and B. A and B, do I need to go over right now? Speak for me, people. A, the percent ionization was 0.06. Okay, B, the ionization was 1.9. And so this is again indicating the differences in how dilute concentrations of acids differ in their ionization. Who ionized more? The concentrated one or the weaker one? Or the diluter one? More dilute one. More dilute one, okay. So it made 1.9 versus 0.06. So who's got me on the Chateliers? Using that as an explanation. Raise your hand. Not everybody at once. I'll ask for one person to get me started before I start. Courtney, go for it.
Okay, so since the concentration's lower, it has to shift to the right in favor of the forward reaction so that more ions can be created to try to balance out the lower concentration.
Okay, so they all have to equal Ka, right? Ka is the point at which Q stops shifting right. So if Q is ever less than K, ever, in any situation, that means we don't have enough products. Not enough products means you need to continue to proceed right. So as you continue to proceed right for something like this, I'm just going to use A minus as my anion. If you have a dilute sample, meaning you have a lot of volume of water but not so many ions, the value of the numerator is going to be really low. Okay, especially when you multiply 2 ion concentrations that are dilute by each other, it gets doubly low because of the way exponents multiply. So you're going to have a lower concentration of ions, and that's going to force you to need to create more ions to get your Q value to approximate K value. Of course, it's going to be too low. So how do you do that? You must shift right according to Le Chatelier's, and as you do that, your percentage of the ions, seemingly you don't think it's going to change too much. It is going to shift right, but as you are taking your ion concentration, which is X, divided by your lower initial, when you multiply by 100, your percent ionization is going to go up because your numerator is higher, your denominator, which is the lower initial concentration, is lower, times 100, the percent ionization is higher. So mathematically, it should make mathematical sense. But then Le Chatelier's is just talking about, is this Le Chatelier's? Right here, okay. And this is a lot of reading, but it's really what we just talked about, how the Q value being too low And so you continue proceeding right or shifting right to make the Q up to get equal to K, which is us making eventually more ions as the shift right occurs. So read that if you need to. And then I think that's it. What you guys asking? 2.6. Okay. I need you to get up and get a kiss candy or stretch because you guys are going to sleep on. Yeah. Because I have some notes to do with you. Oh, I think I looked at B and I thought that was 6. Thanks for telling me that after the fact. Sorry, I looked at B and I thought it was a 6. What part of 6? Here's 6. Tell me where you are. What do you need?
I got 6.
Sorry. Does anybody need 6? I apparently just went over 5. I wasn't watching. Here's 6. Let me know. Okay, we're moving to bases and salt hydrolysis momentarily. All right, so bear with me here. I'd like to get through about 5 examples of good, healthy examples. And then we're moving to practice. That's not AP Chem. All right, talk in your groups. You have 2 minutes, 3 minutes, and explain these to each other. Tell me what they indicate. You have 2 minutes to talk.
Strength of acid or base is strong. Strength of conjugate is weak, and then equal contribution usually is going to be high. And then the strength of bond attached to H is really low. I love my charger. I have it downstairs. Does it have closest to the kitchen? It's like right next to the back door. Not that big of a deal. I just have not had it since I forgot. I've always remembered. I didn't tell you, but like, I forget to tell you. What you thought?
Okay. All right, guys, back with me. Back with me. AJ, what's a large K value mean?
For the relative strength of an acid, it means that it is stronger.
Stronger acid. What does it mean about the strength of conjugate base, Courtney?
Weaker.
Weaker. And what's it mean about the equilibrium concentration of the H plus, Emma? Higher. Okay, or like 100% hopefully, or percentage-wise. And then strength of the bond attached to H, Levi? Weak. Awesome. Okay. And, ooh, tell me this one. Which is stronger? And name these for me. Alvin, what's the name of this? Hypochlorous versus perchloric. Okay, who's stronger? Everyone says perchloric. I know that's because you memorized the strong acids, but why? Because it has more oxygens, and that makes... Okay. Okay, why does it make the bond weaker? Electron density. Okay, more electron density in the middle of the ClO4. That little hanging off H is like, hey, just drop the electron in the electron density. It makes it weak bond. Okay, let's do the KBs. KBs, this is basically It's bad when you do it twice. I think you should stand up. You got 2 legs, right? Okay, stand up. 4 legs aren't working so much. Okay, so bases, I know that we know that's 100% ionization. I'm not going to do a POH problem at this very point in time, but I do want to make sure you could do it from here. If I gave you, and tell me that you know how to, maybe give me the process on this one. If I gave you a 25-gram solution, a 25-gram sample of barium hydroxide, and I gave you that solution, how did you find the pH? Give me steps.
Okay.
Shout them out.
You convert grams to moles.
Sorry. Think about that first, and then I'll ask you more time.
You convert grams.
Think about it first. Just give everybody thinking time. My bad. All right, go ahead, Jacob.
You convert grams to moles.
Grams to moles, and then
Divide by liters.
divide by liters. Okay.
And then you have to multiply that by 2 because
Ooh.
the 2 ratio to the OH in solution.
And you do that because this is a strong base, right? So it makes a 1-to-2 ratio.
Yeah.
So this is going to equal molarity, but then you times that by 2 to get the hydroxide concentration.
And then, you want to keep going?
Keep going.
Alright, then you do negative log of that to get the POH.
Okay.
And then you do 14 minus the POH.
14 minus a negative log of that gives me pH. Yes? True story? Moving on. Okay, that's our POH. Kind of just a quick chat. Yeah.
Or could you like just add 1 times 3 to the negative 14 by that and get the concentration of H plus and then.
Yeah, you actually could do it. The pH formulas are so versatile. You can really do a lot with them. So yeah, she said take this and then use the Kw constant divided by that to give you hydronium, and then go to pH. All right, so then for KBs, KB concentration or KB base dissociation equations are exactly the same as KAs. For this example, this is just a generic way of writing Bs, which are bases. When bases react with water, they pull an H towards itself, right? According to Bronsted-Lowry, they are acceptors. That leaves behind a hydroxide. Boom, that's hydroxide. We're done. What would this make? Be loud and proud. That'd be great. Ammonium and hydroxide. What's the KB expression for that? The whole shebang. Concentration of ammonium
times concentration of hydroxide over concentration of ammonia.
Do you include water? No, pure liquid. If this is a weak base, what can you assume about the KB value? Less than 1. Way less than 1. Okay, and so generally in our iceboxes we can neglect X. Okay, so just make a habit of trying to continually check X though to make sure, especially if you're doing a percent ionization. All right, find the pH of this. Try to set this up by yourself, using your basic knowledge of bases and similar situations to acids. The KB values of the works. Should be writing something down, but I mean, unless you're doing it in your head, I don't think you are. It's not a challenge. I think you'll square this. Give me approximate. something. That's what I was hoping for. I was at 1.5. I wasn't quite sure.
4.24. Times 10 to the negative 4.
It's hard to do square roots of 1.8, yeah. 4.24 times 10 to the negative 4. But you guys could approximate that based on your exponent of negative 7. So, what does X represent?
The concentration
Of hydroxide. That's the key point here. This is not hydronium. This is right, correct?
Yes.
We
Yes.
proceeded. Okay, proceeded. So that's hydroxide. Then how do you find pH? Give me one step on how you find pH. Together.
in 1 step.
Thank you. 14 minus the negative log of, so 4.24 times 10 to the negative 4. What is that?
10.63.
10.63. Does that make sense for a weak base?
Yeah.
Yes, it does, because 1, it's basic. 2, it's not 100. It's not like 14. It's kind of between 7 and 14. So we're looking good here. Okay, that's the only weak base one I'm doing right now. Yes, ma'am.
Wait, how do you say
Oh, how do we do sig figs? Sorry, I am a horrible person for that. How many sig figs are here? 2. How many sig figs should be in my hydroxide? 2. So this should be 4.2 times 10 to the negative 4, which should be how many sig figs? I mean, how many decimals in pH? 2, which is 6.3 here, unless I rounded wrong. Is that right?
Yes, but I have a point.
Yes.
Do you have to like have sig figs while you're doing the problem, or can you like write down like a whole bunch as long as you can't?
You can, you can hold your
So I can have like
numbers out.
6. I can have like 6 right there, but if you have X, but as long as my answer has 2 sig figs, we're good.
Yeah, as long as the answer that's asked for has the correct sig fig, you're good. Yeah.
Gotcha.
All right, so I have one more for you, and it's starting on a different side. So it's not starting off with the initial. No, sorry, it's asking for KB, not the pH. Go for it. What's the hydroxide concentration? 5488.
Yeah.
What's the equilibrium concentration of base morphine? Anybody? 0.015 subtract that.
0.48.
That's it?
Oh, we can go.
Give me one more. Okay, that's fine.
Well, that's 5 actually.
Gosh,
Sorry.
Allie's gonna love my notes. They're so very neat. Okay. Give me a thumbs up if you were able to think about backtracking from pH to where you needed to get to your values for KBs. Most of us pretty good. Okay, so when you given your pH for this instance wasn't really all that helpful because we needed to get the hydroxide concentration. So immediately went from P to POH and then saw for hydroxide. That once it says that is the pH, that is at equilibrium, which I think may have been the only point where you're like, all right, I got OH, but what is that? Is it I, is it C, or is it E? Well, once this thing is mixed with water, it has released a couple of hydroxides, so that is the equilibrium value for OH. So that OH concentration, which equals the cation's ion concentration because of the 1-to-1 ratio, that was the change as well, so you subtract. When you plug into KB, what do you guys get? Because that's not the final. Anybody? 4 point what? Okay. Was that a stronger base or a weaker base than ammonia? Go back to the last problem where we wrote ammonia's KB down. This is morphine's KB. What's ammonia's KB? 1.8 times 10 to the negative fifth. Okay, which one's a stronger base? Loud and proud. Ammonia, because it has a higher KB, which KB is representing the products of the reactant. So if you have a higher KB, that means you have more products. That means you're shifting and you're proceeding to the right often and making more products, meaning you're a stronger base. All right, give me double thumbs up if you're okay with KBs, similar to KAs. I'm sorry. I like to believe in you guys and your little calculating abilities. Can someone give me a more accurate answer? 1.6 what? Times 10 to the...
Or it'd be 1.6 something.
Negative 6? All right, does our conclusion still stand?
Yes.
Yes, okay, I'm happy with that. Okay, so I think I'm going to stop KBs for a moment. Let's look at some more holistic things together with comparison KAs, KBs, and what do they mean together. And then our last bit is salts. So it's 9:40. If I'm done by 10, that gives you 30 minutes to finish up some practice with me, okay? That's my goal. So go ahead and write out your Ka and your Kb for these two reactions in the morning. So your Ka and your Kb. You might need to make your own products, FYI. You maybe realize that though. That was fun. Thanks, Billy.
Okay, so on the K, I put concentration H plus instead of concentration. Would that be considered wrong?
For this exact example, it's not going to work out the way you want to, but normally it will be fine. So, as you're looking at this, you should know that acids have to make hydronium in water, and water is an imperative partner to making acids dissociate. Acids don't dissociate by themselves. They need a counterpart that pulls their H off of them, right? They need something to pull that. So that's why many times I'm trying to make sure that there's mostly water there, or it's evident that it's present. So when you form your hydronium and your ion, and then this one forms a conjugate base and a hydroxide, you should see some similarities between these two Kas and Kbs the way that they're written here. What do you normally do with Ks? Actually, before I do that, let's add up these two reactions, just like we did with our equilibrium, general equilibrium. Add these up, what do you get? as you think about the cancellation of things that are the same on left and right? Maybe first tell me what cancels. Okay, so I hear two H2Os and makes hydronium and hydroxide. What is this representing? What's the word that... Okay, it does represent KW, but it actually represents the autoionization of water. Water and water can exchange an H+, leaving one water with an extra and one water without one. So this is called the autoionization of water. Water can do that, and it does that. And the fun fact that it says in your reading is like 2 out of 2 billion water molecules do that, which is why water is neutral, because it makes equal amounts of these in a 1-to-1 ratio. But that means that if things are in water, you'll always have hydronium and always have hydroxide. All right, so when you add reactions, what do you do to the K values? You multiply them. Remember that? You don't add them, you multiply them. Well, if I multiply these like this, let's see what cancels. You guys tell me. Maybe I can write this again. Let me write it down here. So I see hydronium and anion over HA times HA, hydroxide, and A minus. Who cancels? The A's and the HA's. What's left? Hydronium and hydroxide. Hydronium and hydroxide. Shouldn't that be what it equals? Okay, so this is the combination, and this will always work. KW is equal to KA times KP. So you will use that 5 times more today at least. But this idea is that if you have the Ka of an acid, the reverse of it, so as you probably noticed here, this is my acid, this is my conjugate base. What did I do is I made this conjugate base interact with water, and I forced it to do what it could do. Well, it didn't have another H to give, so it had to act as a base, true? Right? So it had to act as a base, so it did. So I have given you the Ka of an acid, but if I give you an acid, I'm like, hey, make it act as a base, or make the ion that it creates act as a base, I'm going to give you the Kb for that base. I expect that you can get the Kb from the Ka and Kw. So how would you get Kb from Ka and Kw? Good. So Kw over Ka equals Kb. So you could actually calculate the true K value of what A acting as a base is. So the Kb would be what you calculate here. Plug it in. We're going to do that a whole lot. Okay. So that's a true statement for any acid conjugate base combination, or any base conjugate acid combination. So if I ever don't give this to you, well, if I can get this on the board, okay, for any acid-base conjugate combination, if I give you the Ka, you can automatically get the Kb, or vice versa. If I give you the Kb, you can always get the Ka by using the relationship between Kw, Ka, and Kb. That's okay. Okay? Sorry, I said K. Okay? Potassium? Let's do this. All right. Moving to salt hydrolysis. Last topic today. So this is in your reading. Go ahead and look at page 18 through 19 and skim that for about 3 minutes. And then I want to hear if you remember some of this from honors chem before I move on. Page 18 through 19. Scan that for yourself for now. I have dog stoppers. No, I want to. Your brain doesn't work on the first glucose. Your body takes too long to break glucose down, so I'm stopping your brain. See, Levi, if I eat all that, do you want me to be fat? But I'm just trying to spread the love. I feel so bad. I don't anymore. It's been a long time. I haven't in a while. I need to go. So my mom's going to tell me.
That's why you need to exercise, because you hog the town, you exercise, and you just get out of the house.
She's coming today at 5 o'clock, and I was like, surprise! I'm not done with tutoring until 7, Mom. What are you going to do for 2 hours? She got out of school today, so she's out of school in like 2 hours.
Why are we saying a school for an extra day?
They started like a week before us. Our mom's school.
Even still.
Okay, give me a thumbs up if you slightly perused the reading.
You know, this time last year we weren't in school.
I know.
I'm having trouble here, sorry. I was gonna throw it away, it took forever to open it.
Okay. So, in terms of salt hydrolysis, a salt is a fancy name for an ionic compound. Okay? Ionic compounds, which are salts, come from the combination of, anybody? Acids and bases. So, you should remember acid plus base, you have salt and water. That's a really generic way of writing it out. But if a salt comes from an acid and base, I like to say baby salt, okay? Baby salt comes from dad, acid, and mom, base. Well, their strengths determine the pH or the acidity level of the salt. Each of the salts can either be acidic, basic, or neutral, based on where they came from. So you must think about where they came from to recognize kind of the general realm, is it going to be acidic, basic, or neutral. But on top of that, you can do calculations with that, which is now the more advanced way of, in honors chem, we just said, hey, it's acidic, basic, or neutral, but in AP Chem, we must calculate with that. So as you're thinking, let's go ahead and think about some of these that are down here. This is exercise 20 on there, if you want to write it on there. Where did sodium acetate come from? Where are the two ions from? Sodium came from sodium hydroxide, likely. Okay, so sodium came from sodium hydroxide. Acetate came from, okay, and who is, give me the descriptor, strong or weak? Strong base. This is a weak acid. Automatically, you should be able to predict the acidity of the salt. It is basic. Okay, now you can't predict the, necessarily predict the pH because it does depend on the concentration, but you know it's basic. It's a pH above 7. So the cation anion is predictable. But then on top of that, you must understand that the ions are all mixed in with water. Water is going to be a reactant for these because it's salt hydrolysis. What's hydrolysis mean? Breaking apart with water. So hydro means water, lysis means to break, breaking things apart with water. So let's break this apart with water. I'm going to just do with A, stick with A so far. So sodium ion can react with water, as can acetate. When I react sodium with water, what does it make? Sodium hydroxide and, so I'm just going to say H plus because I only have, and I'm going to write this as HOH. I think HOH is much more visually friendly. So the OH combines with the Na, leaving behind H plus. Seemingly acting acidic. True? Because despite that I have sodium hydroxide here, there's not a free hydroxide. No free hydroxides, it's not basic. It seemingly acts acidic. This one makes acetic acid and, say again? A hydroxide. Okay, so what we have to think about is like, okay, truly both of these ions can react with water. They can do something. But you know that immediately when you make a sodium hydroxide, it's not going to stay sodium hydroxide. What does it do? It's 100% ionization, right? It's not going to stay like this. It's going to revert back, and it's going to make hydroxide, which is present within water, and sodium. So it's going to 100% reverse its reaction. So we thought we made H pluses, but we don't. It doesn't happen. It just doesn't happen appreciably. It's going to reverse the reaction because it's a strong base. It will not stay like that at all. This, on the other hand, is a weak acid. Will it reverse? Nope. So we're going to make free hydroxides. This is the reaction that we would use to find the pH of the salt. If you have a strong, or if you have a cation of a strong base, it's not going to be an important half reaction that would be important to find the calculation of pH. You must use the one that makes a weak product in the hydroxide, or whichever one's being made. Yeah?
Does this like determine whether or not a salt is edible?
No. I don't think, what makes it edible?
Because if it's, because the neutral one, like sodium chloride, comes from sodium hydroxide
And hydrochloric acid.
and that's edible.
Well, so is lithium chloride, which is people who have high sodium problems. Well, you eat like vinegar, right? That's acetic. Oh, that's acetic acid. Hold on. Don't eat sodium acetate. That'd be like really bad for your throat. I might look that up. Because some of they do react with water in your body. That's actually part of the medicinal chemistry course I took this summer, and I forgot a lot of that. So we'll get to that soon, Jack. Yep, we'll get to that soon. Okay. So off the bat, you should be able to identify the solid as acidic, basic, or neutral based on common knowledge. Secondarily, you should write your two, I call them half reactions, but that's just because I'm breaking it down, and look for the reaction that actually occurs appreciably. We're looking at this one. This is the conjugate base of acetic acid. Okay, this is where it gets tricky. And so this is the conjugate base of acetic acid. Don't we have the Ka of acetic acid from yesterday? You wrote it down for homework. What was it?
1.68 times 10 to the negative fifth.
Yes, negative fifth. Okay, this is not acting as an acid. You cannot use a Ka. You must use its Kb. Let's find Kb from the Ka. Kw over Ka. 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5th. 5.56 times 10 to the negative 10th. Please tell me that's great. Somebody calculate. Memorize it, yeah. I did not do that in my head. I did that in my head, guys. Boom. Can someone verify that? Thank you. That's our Kb. Thank you. Okay, sometimes I memorize different constants for different things. So this is our Kb. I need to set up my ice box in accordance with a concentration. I didn't give you concentration, or did I? Let's do 0.25 molar. Okay? It's you to put parentheses, my dear. Yeah, you watch those parentheses. Okay, so I'm going to tell you the concentration is 0.25 molar of that solution, that salt solution I had. Let's solve for the pH of the salt. Go for it. I think you got it from here. That means you should write something down, or at least pretend you are, to make me happy. Or mathematically solve it. You know, bring them. You guys have any healthy requests? You guys bring in snacks. Let's bring in snacks. If you want to bring in snacks,
I'll say I will.
I'll say I will too, but my mom's bringing snacks, so I don't know what's going to happen when we get home. I'm sorry to distract you. Finish solving this problem. I have 2 more for you after this. Oh, Levi, you have a pH? Solve. Huh? And I'm doing the full out icebox. You guys know you can just do the E at this point because it's still addition and subtraction. I think you've got that. You're pretty smart. You better get X for me. Yeah. 1.1. Negative 5th. Can I get a second on that? Thank you. I usually have to ask that because I don't trust you. Because I'm bringing butterfingers. Okay, what is X representing? Concentration of who? Hydroxide, right? Hydroxide that's being made. So that's nice for you to write down. And then how do you solve for pH from that? 14 minus a negative log of 1.18 times 10 to the negative 5th. Oh, I don't know if I've told you this estimation trick. The exponent controls the pH. Yes, because it's like base 10. pH is base 10. Just like in logs, log base 10 equals X. So the exponent controls the pH. The exponent controls the maximum pH. The maximum pH, or in this case, which is pOH, is 5. So you should estimate that's closer to the 4 side. So that should be like it's more basic. 5.8, what is that? I mean 4.8? 4.9, okay. So that's 4.9-ish. 14 minus 4.9 is 9.1. Is that a good weak base? Yes, it's a even weak, well, actually, no, it's not even weaker. I made up the concentration of 0.25, but it's a weak conjugate base from the ion of the salt. Okay, I'm going to stop there for a moment, and you guys can work on looking at, let me tell you where you are in your packet. If I find my packet. You guys see where it says salt hydrolysis, AP Chem? It's right underneath the acid notes. Salt hydrolysis. So skip those two little examples at the beginning. I'll do those later. It says, what is the pH of blank 1 through 8? Okay, so I want you to start with a couple from there. You'll notice, though, are all of those salts looking out? Does everybody give me a thumbs up if you see practice 1 through 8? 1 through 8. Are all of those salts? So the answer is no, not all of them salts. You need to think about when do you do salt hydrolysis, when do you do weak acid Kas, when do you do weak base Kbs, when can you do strong acids, and when can you do strong bases. There are 5 or more now types of problems you're able to do. So start on 1 through 8.
Only one strong base. So, strong acid or strong base? You said yes.
Sometimes you'll find that both of them. So Lucas just asked a couple of good questions. I'll go over those at the end of class, okay? So there's more to salt hydrolysis than just that, but that's a good start. And you guys saw the extensiveness of how I showed my work. You don't have to be quite as extensive as me, but you do need to show 100% of your thoughts there, okay? So show me some stuff so I can give you some actual good feedback.
Are you going to give us like the
What K? Can you tell me? Because I'll write them on the board. It's in your textbook too, so I'll always find out with. Which one do you need? Oh, you need a bunch of them. How about, hold on. If you guys want a list of this, let me see a copy. Let's make a copy of the KAs.